All right, hello everybody. This is week 5, the end of week 5 here in Algebra. Algebra 1A, in case anyone was forgetting that. So far, this unit we've been talking about a lot of different ways to graph equations, standard form, slope intercept, point slope. Tuesday, we dove more into writing equations, and we figured out how to write equations from 2 points, from a graph, when we're given the slope and the intercept, and from slope and 1 point. There's one more style of process to write equations that we need to look at today. Anybody have a guess as to what that might be? Probably not. That's okay. Wouldn't expect you to. Now I got to get on the right screen. Okay, now I got on the right screen here. I just was asked if that was like a T-chart, and that's exactly what this is. This is an example, of several examples actually, of being able to find slope from a table. Sometimes they're called data charts. If you're writing them out by hand, it's called a T-chart usually, because you can just make it like a lowercase t. Two additional things that I don't know if we've talked about or not. A couple of vocabulary terms. Do you know what all of the x values are called? Well, the example that we have are integers, but that's not the word I'm looking for. And that was a good try. Starts with a D. No, denominators and fractions. It's actually what's known as the domain. The domain includes all of the x values. And so whenever you see these kind of T-charts or these kind of data tables, the x values are always on the left-hand column. That's always the domain. The column of y values has a different designation. Any guesses on that one? The end domain. Well, that's not a bad guess, since the y values depend on x. At least in our equations, we plug in x and we figure out what y equals after you do the calculations. But the y values are always called the range, the domain and the range. Yeah. Just talking in general right now about what these tables are. We're gonna be able to figure out the slope and ultimately write an equation from any of these tables. This is like the fifth different way information can be displayed, where we got to know how to write an equation. The other thing that this will fold into today is we got to start looking at how we determine if an equation is actually a function or not. In other words, does the y value automatically come from x, or is there more than one possible y value when you plug in x? What's the shape of the graph look like? That sort of stuff. So got a Khan Academy video we'll look at here in a minute. But I need to pause here for a second to copy this first table down here and put it in a Jamboard. So bear with me. All right. So back to the tables here. Got two different examples. Can everybody see both of these tables at home? First of all, I want to be sure I'm sharing the right screen.
Yes.
Okay, great.
Yes.
You notice anything about any of the ordered pairs? Because that's all these really, this is just another way to show ordered pairs, right? You got XY, 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 05, 110, 215, 320, etc. So those are all ordered pairs. Do you see anything in there that from those ordered pairs that might be helpful in graphing? The range, oh, wait a minute. Did you just say the range is by 5 and the domain is by 1? Wow. You want to teach the rest of this? Because that is awesome. Yeah. Not and still be a function. That's right. Tony's pointed out something here that we'll get into in a minute. If we got two different y values with the same x value, it's not a function. We're getting a little bit ahead of ourselves. But Jessica correctly noticed that when you start looking at these, go down the list here from one y value to the next, every one of them is changing by 5. And it looks like a +5. On the y, on the side of y, they're all changing by 1. That also looks like it's positive. Huh? What? Did I say y twice? Oh, sorry. On the side of x, it's 1. Yeah. And she did. That's good. That's what I want. So, well, I won't be able to answer. So domain and range. Put those up above the columns to make sure that's somewhat helpful. And it looks like the y values are changing by 5 and the x values are changing by 1. So can we say the slope is 5? Okay, how do we know if it's positive or negative 5? That's the only issue. Yeah, Tony. Okay, if it's increasing or decreasing, are you starting at the top of the list or at the bottom of the list? Okay, but what if I wanted to start at the bottom and go the other direction?
Wouldn't it be positive because technically you don't have any negative numbers?
The fact that there's no negative numbers doesn't matter, but what I was trying to trip Tony up here, he's correct in saying start at the top and go down. These are all increasing. Well, if I did it the other way, if I did the opposite, now everything is decreasing. So it's -5, -1, -5, -1, which is still going to end up as a positive, right? Because now we got a negative being divided. The change in y is going to be negative. The change in x is going to be negative. So the negatives cancel out. So that's a good observation. The thing I was hoping somebody would see was this first order pair, 0, 5. Because in our graphing, that combination is extremely important. Because what do we have when x equals 0? It's the y-intercept. It's the y-intercept. Every time you see, and part of the reason why I picked this one is because of that example. If you remember the definition of the y-intercept as x equals 0, we don't even know what the equation or anything is yet, but we can identify that as our starting point. erase my circles. It's kind of messy looking. Do you? Oh, that's nice. When X is 0, then you have the Y-intercept. Whatever Y is, that's your starting point. And if you think about how slope-intercept works, Y equals mx plus b, when you plug a 0 in there for X, it doesn't matter what the slope is because anything times 0 is still 0. And so then you end up at Y equals b. So if you got a number there for b, or you got 0 or whatever, that still is your Y-intercept. So if I wasn't as observant as Tony and noticing that this is progressing and Jessica progressing in a positive manner, up 5 on the Y column and up 1, I can take any 2 points and do the slope calculation and come up with the slope. So the easy one would be to take the first 2. Change in Y, 10 minus 5 in the Y column, and 1 minus 0 in the X column. I still get 5 over 1. Kind of confirms that it's a positive slope of 5. And that's the reason I did that is because that's really the one thing that you should do if all you have is a table, because you don't have a graph, you can't see the line. If you're not convinced or you're not sure about if it's a negative or positive slope, then just pick a couple of the points and do the calculation. So what if I took the last one and the first one? 30 minus 5 and 5 minus 0. 25 over 5. And that's going to reduce by 5. Still gives you the same answer. Okay, so to write the equation that goes with this table, okay, let's say, for instance, I recognize that I have the Y-intercept. So I know that Y is going to equal B. I just figured out the slope. So the equation is Y equals 5x plus 5. But if you didn't recognize that 0, 5 ordered pair as the Y-intercept, now it's just like any of these other ones where we use a point and a slope, or we use 2 points because we had to find the slope first and then use a point. So let's go back and use the form of Y equals mx plus b and do the substitutions. I'm going to use the very first number, the first order pair. 5 equals, my slope is 5. We just calculated that. X in that order pair is 0 plus b. Now I'm finding b again. And because 5 times 0 is 0, I get the same answer, 5 equals b. So just because you have a table, it's exactly like when you write an equation from 2 points, right? Because you always have to find the slope first anyway. And we could have picked any of these ordered pairs here and done this substitution and still gotten the same answer. Questions about that? The other thing that is helpful about tables, my little jagged, my jumps from one line down to the next here with these little mountain ranges, that is just my way to visually identify the change from one line to the next. And it helps me identify whether or not there's a consistent change. Because if there's not a consistent change, then I don't know what we have. We might have some different shape. It's probably not a straight line. we're not going to be able to find the accurate slope. It might not even be a function. Might be some other just kind of random relationship between the numbers. And so by sort of walking my way down this table from 5 to 10 to 15, etc., I can see the consistent change between each two numbers in the y column. See the consistent change in the x column also. And again, slope is change in y over the change in x. So what would be the slope in our second problem there? It's problem number 2. You got it already, Tony? What do you get? Okay, Tony thinks it is -6. Well, certainly the x column, it's obvious to say that that's consistently changing by -2. If you start at the top and go down, right? -2, -2, -2, -2. So yeah, it looks like the change in x, I'll use my Khan Academy triangle symbol here, delta, -2. Change in y. Did you compare these two columns then, Tony? Okay, well, I'm beginning to wonder about your slope, because I see down 6, down 6, down 6, down 6, down 6. I'm with you that the change in y is -6, but I don't think that's the slope, because we still have to do that comparison, right? The change in y over the change in x. So if I just took these numbers, it looks to me like the change in y over the change in x is going to give me a slope of 3. But I don't trust myself, so I'm gonna pick these two right in the middle here. So I'm going to do the calculation. 4 minus, this is y2 minus y1, x2 minus x1. So I started with 4. Somebody else got 3? Okay. All right. Okay, cool. So -4 minus -6, which means these become positive. And I'm going to get 6 over 2 again. On the other way I did it, I got -6 over -2, but it gives me the same result, -3 or +3.
Yeah, I did 10 minus 4 to -4.
Okay, great. Yeah, and it doesn't matter which two, any two in the columns will work. You still should come up with the same calculation. So we got the slope. We don't have the y-intercept though. We still need that for slope-intercept. So that's when you go back to y equals mx plus b and start substituting. I'll just pick I'll use the first one, 10 for y, substitute that, the first ordered pair. Slope is 3, x value from the point, -2 plus b. So that is 10 equals -6 plus b. So I got to add 6 to both sides to cancel that. Well, that's a high y-intercept. Okay, so now I got the y-intercept. y equals 3x plus 16. Anybody notice anything about that y-intercept that you could tie back to the table? This is one of the things you nailed it again. Are you sure you don't want to teach the rest of this?
I am sure.
She thought about exactly what I was hoping someone would identify. Remember, in the table, we've already established that there's a consistent change. We were going one direction, but if we continue, if we go the other direction, what's the next number in the sequence? We're going to add 6 and we'll get 16. On this side, the next number in the sequence would be 0. 0, 16. That is the y-intercept. When x is 0, we got the y-intercept. So eventually, you will come up with the y-intercept if you just keep filling in numbers in the tables. I mean, that's another way you could do it if you didn't want to do the calculation or do the substitution work. Okay. Questions, anybody? And that's really all there is to all of this stuff with tables. You know, as many different examples as you can imagine. It's all the same process again and again. Yeah, Tony?
For the actual problem with the y equals you ever show me more of that? How to do that?
What do you mean, this one down here?
Well, yeah, but plugging in the numbers as far as getting like the actual answer. That's what
You
it
would
is.
subtract 10. Or you would
What?
go with the math, and then you would have to go to the group, and
We got -6 on the right-hand side. We got to cancel that. Remember, because we created a one variable equation when all we got to find is b. When we did all the other substitutions, the only thing left is b that we don't know. So at that point, it's just to get the b isolated. It's just like any other equation solving. You do the m and the x, that's multiplication, right? That's 3 times -2 on that one. And so that becomes -6 on the right-hand side, which we got to get rid of in order to get the b by itself. So
And that's the part that I was struggling with. I wasn't sure if I had to multiply.
well, when you see, I don't have them directly together, but if you're in, it doesn't want to let me in there. Remember this structure right here, mx, when those letters are right together, there's only one possible operation. It's multiplication. And so we solved for m. We figured out that m is 3. Right? That's what all this calculation, all that other business with the table was. So I just substitute that in there. So once you do the substitution, you still have to do the operation that was there before. So since m was times x, no matter what I put in for m and whatever I put in for x, I still got to multiply the two. You know, we don't use x anymore to show multiplication. When I got two terms right together, I see that as multiplication. I could have used like a little star or a dot, or put both of them in parentheses. You know, it's all the different ways that you can think of to show multiplication are possible. It just depends on what you see. So the operations you still have to do even once you do the substitution.
Would you do the 6 under the, when you do 3 times 2, 6? Then you add 10 plus 6 is 16, and then you did b. What do you do to the 6 that we multiplied? 3 times 2, what do you do to
I didn't do 3 times 2.
I think I get what she's saying.
That's when we multiply 3 times 2. we got
Okay,
6.
look at it closely, Kapana. I did not multiply 3 times 2. I multiplied 3 times negative 2. That's negative 6. 3 times negative 2 is negative 6. In order to, that's what we were just talking about, in order to get the b by itself, this is the opposites. This is where opposite operations come in. How do I get rid of that negative 6 from the right-hand side? What's the opposite of negative 6 that's going to allow me to cancel that term? It's positive 6. And if I do it on the right-hand side, I got to do it on the left-hand side. This is exactly what you and I have been going back and forth on those your texts that you've been sending me pictures of and stuff. Because it's all the opposites. But if you didn't see that sign there, if you didn't see that minus sign there, that's going to throw you off for sure, because signs are everything. That minus sign is it's the boondoggle of all these problems, because if you get it wrong, the rest of it's going to be wrong. Yeah, so if I had to rewrite this, I can't get the thing to let me go back in there. This becomes 10 equals negative 6 plus b. I just kind of skipped this step because in my mind, I already know that that's negative 6 there that I'm going to have to cancel. So the next step in either case is the same. I still got to add 6 because that's the 0 pair. Remember, if all we're doing is canceling a number that's a negative, we're going to use a positive, and vice versa. 0 pairs plus for the minus. Really good question, though. Anybody else got questions? Let's hear it. I like questions. Okay, the next thing that we're going to look at is what they call function tests. How do we know if a table full of numbers like that, or an equation or a graph, is actually a function? Now, function is a strange kind of English word in a way. Where'd that go? Because not everyone uses it the same. When we talk about functions in algebra, what it really means is that one thing depends on another. One value or one statement depends on what you do with another one that precedes it. So if you think about the equation y equals mx plus b, the y value always depends on everything else to the right of the equal sign. So that's why we say for our purposes with these straight line graphs, y depends on x, because if your equation is y equals 3x plus 2, you're going to get a different value for y every time. And so we got to figure out ways to determine, like just from the numbers, if something is a function or not, or if we map it out, or if we have a graph. Okay. So I'm going to go back and use a T-chart again to try to show a little bit more about function, why we can say y depends on x. X is here, y is here. So let's say our equation is y equals negative 3x minus 5. Okay, Now, if I'm doing a chart like this, now I can already graph this. But if I need some points to work with, if I want to draw a line from the points rather than from the equation itself, because if I'm going to graph it from the equation, I already know what to start with. I start here, the Y-intercept. That's going to be my first point on the graph. It's going to be -5. So somewhere down here, -5, I can put a point. Okay, that's one point that I automatically know in the equation when x is 0. Because again, I'm substituting in for x. I'm going to do the -3 times x, -3 times 0, -5. Well, y becomes -5. If I'm doing a t-chart though, and I'm just trying to come up with some ordered pairs, I will almost always use 0, 1, and -1. Because that's going to generate, each one of those is going to generate a separate value for y. And simply by substitution, I'm going to come up with some values that give me ordered pairs that are going to hopefully line up in a straight line. Since this is a linear equation, so if I plug the 1 in here for x, -3 times 1 is -3 minus 5. That leaves me with -8. So where's 1, -8? 1, y -8's down here somewhere. So when I plug in -1, -3 times -1 is +3 minus 5 leaves me at -2. So x -1 down -2. I don't have a scale on this graph, but you can kind of see them already starting to line up. And the thing is, we can use any numbers that we want for x. And this is a sort of a demonstration of why slope-intercept is a function. Because when you put a number in for x, you're going to get one answer for y. One possible answer and one answer only for y. Because it's just multiplication. It's doing the operations that involves x. Sometimes these kind of linear functions, I don't know if you've ever heard this or not, but some people will call them input output machines. Pop machine, that's going to be my example.
Push the button and give you something else that's not, it gives you the actual one you need, and there's only one solution for that number.
Yeah, pop machine, vending machine, you put in your $1.50 or whatever, you push a button for the Diet Coke and you're going to get the Diet Coke. That's a function. What you get is a function of what you put in and what you press, which button you press. Nobody would ever go to a vending machine if they put their money in and press one button and they might get this or they might get that or they might get something else. Well, I don't know about that. I mean, you have to maybe
I mean, if you put money in there,
shake the machine.
you get a drink, and then something else comes out.
Oh, a second thing. Well, see, that's still not a function.
That's happened to me before.
So that's part of the reason why these things sometimes get called input-output machines. Because the output depends on the input. Questions so far? All right. We'll go back to these examples. Here's where domain and range comes in again. And when it says list the domain and the range, now all we're doing is putting the list of numbers together. The domain are all the x values. So for number 11, this example here, our x values would be 3, 4, 5, and -3. The range would be all the y values, 5, 8, 15, and 12. Okay, so anybody know whether or not this is a function? We got one vote for yes. I'm in that category too, so it makes 2.
Yeah.
All right, Jaden thinks it's a function also. The easy way to tell when you have a list of domain and range numbers, or even the mapping, I'll show you in a minute. If you have repeating x values, you do not have a function. So we don't really care what the y values are, but if that x value repeats, that means I got 2 different y values for the same x value. Well, that's not a straight line. That's some other kind of shape. That's not a function. So that's one way to prove whether or not we have a function. If we have any repeating x values, it is not a function. Yeah.
So for the domain would be 3, 4, 5, -3.
Yep. None of those repeat, so that's a function. And if all you have are the points, that's one of the easiest way to determine whether or not you have a function. Just look for the repeating x values. If there are no repeating x values, then you do have a function. Another way to show the same kind of thing is a mapping diagram like this one. The domain is in that box on the left. The range values are on the right. I don't see any repeating x values. I don't see any repeating numbers in the domain. So I'd say that's a function. Yeah.
So like for the 10 and 6, say they're both Coke. You push that and you get the same answer for both. So it is kind of like a vending machine when you look at it like that.
Could be. Have you seen vending machines though where there's more than one button just for Coke?
Yeah.
Yeah, heck yeah.
5.
The most popular drinks in some of these, pop machines will have, at least 2 sometimes. Heck, I've seen some machines at like resorts where it might be all Pepsi. Every button is Pepsi.
I found a mango Pepsi yesterday.
You did? Oh, I'm sorry.
It was good. I like it. I like it.
Mango Pepsi.
I'm not. Pepsi's the best.
Ah.
Mango Pepsi.
Hey, can I get an egg inside your Diet Coke right along with you?
I can't give you an A for that, but I'm really happy to hear that you like the Diet Coke as well.
Pepper grade. Yeah, Diet Coke is one of the best sellers I've
All right, I'm going to get back on topic here. We got to talk about soft drinks. You can tell it's the end of the week. Everybody's ready for something else. So in 13, you see 4 different types of graphs. And it's asking which one is not a function. The what? The last one? Why would you say the last one? You're right, but I'm curious as to why.
Because they're both going off that way. It's not a straight, or not, I didn't mean straight, but it's not a line.
Well, neither is 1 and 2.
I was gonna say that. I don't know.
It's okay, though. You picked the right one.
I don't know why.
Have you ever heard of something called the vertical line test?
Oh, yeah.
No.
Yeah.
Okay. When you have a graph, that's what you need to use. If you go down any of these grid lines here, straight up and down, vertical line, and your vertical line touches the graph line more than once, it's not a function. And that's why that one on the right here, the far right, is not a function, because at any point on these curves here, this is a parabola, this is a kind of quadratic function. That's next term, you'll get into it. So if I picked the x value of 1, right, this first spot on the graph, I could have a y value of +1 or a y value of -1. So just from the graph, you can also tell that I got two different x values, or the same x value for two different y values. So that's a repeating x value. So I got this point here, 1, 1. I got this point 1, -1. Follow that line out here. Let's see, that's 1, 2, 3, 4. Same thing, 4, 2, 4, -2. Any place that you cut through that graph line more than once, it is not a function. That's the vertical line test. Of course, the third one, we know that's a function because that's all we've been working with, these straight lines. Y equals mx plus b gives us a straight line like that. 13, the first one, that's another type of parabola. That's a quadratic. It is a function. It goes down and it spreads out, right? You don't have any repeating x values on that one. It would pass the vertical line test, exactly right. Same for this S-shaped one here too. It'll come really close to looking like you're hitting the line twice, but close doesn't count in algebra. You know, it's got to be exact. So those are the two real big ways to determine if something is a function or not. Let's see what the other sheet had on here. I'm not going to spend a whole lot of time on this particular handout. It is in your materials because all we're concerned about are linear functions. There's lots of different types of functions that aren't straight lines. You'll see that as you go on in algebra. Here's an example, another similar example from the tables like we were doing a minute ago, looking for that consistent change. In example number 1, we got it. In example number 2, there we don't, right? The y values are jumping from 15 to 33 to 51. That's oh, wait a minute, I'm wrong. That is 18. I did my math wrong again in my head. I wasn't thinking that was consistent. So those are both linear. Nope. I was right the first time. I didn't read this correctly. If I look at just the y values, that's what these numbers out here represent. It's not the difference between the blue numbers. It's the difference here in the y column. That's a difference of 15. Then there's a difference of 33. Then there's a difference of 51. That is clearly not changing at the same rate. So that was my bad. Sorry. The next page just gives you a bunch of other types of graphs that show linear or nonlinear. There's only one in this grouping of 5 here that is a linear function. It's the one down here with at C. All these others are functions, but different types of functions. Believe it or not, this letter E, that's still a function. Because you're not going to be able to fail the vertical line test even with that one, as strange as that may look. So there's some other examples in here. If you look at this one for problem number 7, it talks about tigers. It says use the table to determine whether the minimum number of calories a tiger cub should eat is a linear function of its age in weeks. Not really. That graph does not represent a straight line. Linear means straight line. So if it's got any kind of curve, it's nonlinear. So the fact that this tiger cub has to eat increasingly more calories is not necessarily a function of its age. It could be because of its size. It could be just because of its diet, its location, how much activity it's getting. It could be related. There's a relationship there between calories and age, but it's not a one-to-one, put in the calories, get the age, or get the age, put in the calories. It's not the same as a function where one thing directly influences another. You know, people look at weather, they'll say that the temperature is a function of sunshine, but that's not really a function either, because it's not just dependent on sun shining. Because we get bright sunny days in the middle of winter and it's freezing cold. If the temperature was just a function of sunshine, anytime the sun was out, you'd think it would be warm. But the rotation of the earth, the tilt of the earth, the position relative to the sun, all that kind of stuff, where you are on the planet, all of that goes into making weather, your wind patterns and all that sort of stuff. So it's not just a one thing. So people say one thing is a function of another a lot of times inaccurately, because there's more than one factor involved. For us, with linear functions, we got a direct connection. We put in one thing, we get out another. Makes it simple. So I want to look at this Khan Academy video next. I gotta find it. And it's hard. You can't be here the whole time.
We're asked, do the points on the graph below represent a function? So in order for the points to represent a function, for every input into our function, we can only get one value. So if we look here, they've graphed the point, looks like -1, 3. So that's the point, -1, 3. So if we assume that this is our x-axis and that is our f of x axis, and I'm just assuming it's a function, I don't know what it really is just now, this point is telling us that if you put -1 into our function, or the thing that might be a function, or maybe our relation, you'll get a 3. So it's telling us that f of -1 is equal to 3. So far, it could be a reasonable function. You give me
Now, if you notice, he's talking about f of x and f of -1. What Sal is writing out here is what's called function notation. You know, our y equals mx plus b equation could actually be written as f of x equals mx plus b, because all it means is the function of x, whatever you put in there for x, is going to spit out your y value. So f of x and y in our sense means the same thing. And that's what he's doing here. If you notice, he's got the -1 plugged in here for x. So the way you read this is that if you have a function where your x value is -1, you're going to get 3 as your output for y. We don't deal with function notation very much in this term, if at all. You'll see it more next term. So, but that's all that means. F of x means function of x.
-1, and I will map it to 3. Then they have, if x is 2, then our value is -2. This is point 2, -2. So that still seems consistent with being a function. If you pass me 2, I will map you, or I will point you to -2. Seems fair enough. Let's see this next value here. This is the point 3, 2 right there. So once again, that says that, look, if you give me 3 into my function, into my black box, I will output a 2. Pretty reasonable. No reason why these points can't represent a function so far. Now, What about when we input 4 into the function? Let me do this in a new special, let me do this in magenta. So what happens if I input 4 into my function? So this is 4 right here. Well, according to these points, there's 2 points that relate to 4, that 4 can be mapped to. I could map it to the point 4, comma, that's 5 up here, 4, comma 5. So that says if you give me a 4, I'll give you a 5. But it also says if you give me a 4, I could also give you a -1 because that's the point 4, -1. So this is not a function. It cannot be a function if for some input into the function, you could give me 2 different values. And you can see that right here. An easy test is to just see, look, for one value, I have 2 points for this relation. So this cannot be a function. So this is not a function.
And so right there, showing this in function notation where you've got the X value repeating, he's showing that it's not a function because now you got 2 different Y values. And then he confirms it by using the vertical line test. So all the stuff that we've been talking about in the last couple minutes is in this 2 minutes and 22-second video on Khan Academy. Yeah, look for the test to come out this weekend, all right? Questions on that from anybody? Khan Academy, Sal Khan, you got to go there, get an account. Oh, you should, yeah. Yeah, get in there, start working. So one more thing I want to show as we approach the test. We haven't had much time to do this kind of thing in past units. But since we got a little extra time and today I'm going to kind of skim over this a little bit. When we are all in class together, typically we will do a practice test on the day before a regular test. With this being virtual, we don't really have the opportunity to do that. I still have it set up so that you can take the test twice. You know, it'll be 2 different versions of the same kind of material. So this, perhaps, if we were all in class together, could be a practice test. Most of them historically have started off with a page full of vocabulary. So all the terms up in this box: rate of change, slope, Y-intercept, X-intercept, slope-intercept form, on and on and on. You should have some knowledge of now after 2.5 weeks of working on this stuff with graphing. So this can be a good thing to practice with also. They're giving you the form of the equations. A problem like this, though, a line that slants downward from left to right has what kind of slope? How are you going to answer that? I always need to visualize it. So if it says downward from left to right, if I put my left hand up in the air and go across my body downward to the right, that's going to give me a negative slope line. So sometimes you might see some definition problems in the test that include stuff like that. Here's some other examples of the kind of the function test.
Can you scroll back up to the graphs for a second? So if you have that, the one that's got the circle on it, that would be a non-function, right? Or no, that would be a function because it only touches the lines once.
The big circle there in the lower right?
Yeah.
Okay, Jesselyn says that's a function. Anybody want to argue with her? I don't know how that passes the vertical line test. It's not a function. You draw that line through there, it's going to touch that circle twice somewhere. Any place you draw a straight line up and down. Now, the thing about these, I thought you were going to ask me about these first two. These are weird looking things because they got some closed circles and some open circles. Remember what the closed and open circles mean?
Greater than equals.
Well, that's where we saw them, but are they included or not included?
No.
Well, which one? Open circle or closed circle?
The open circle is not included.
Open circle is not included, closed circle is included. So that kind of graphic, that kind of symbolism is still at work here, even on these graphs. So if we were doing this on paper, you get a chance to graph some slope-intercept equations, just like we've been doing, starting at the Y-intercept. Those first two both have a positive slope. So which direction would the line go? Up to the right. Very good. 3 and 4, what are you going to do with those? Velma, you know about what to do with these now.
I didn't like that laugh. He's like,
Solve for y, right? Yeah, solve for y. Because those are in standard form. We got to convert them. You know, maybe you can substitute zeros and do some calculating and come up with the intercepts. That's another option. That last one there, number 5, that's one of those specialty lines.
It could just be 3.
Okay, what's it look like? What's the graph look like? I'm with you that it's on x equals 3.
The line goes up and down.
Straight up and down, that's right. That is a vertical line. Don't forget, every vertical line is undefined slope, and they all start like that. They all start with x equals some number. So you would go over on the graph here to where x is 3 and draw a line straight up and down, because every point on that line is going to have an x value of 3. It's going to use all the y values, but the x value is only going to be 3. And that actually is not a function. Vertical lines do not represent functions. They won't pass the vertical line test, and it's the same x value over and over and over again.
So it has this on it.
They got to have some slope to them. Even a flat horizontal line can represent a function because it'll pass the horizontal line test, I mean the vertical line test, and you won't have any repeating x values. So you might see problems like this too, where you got to find the slope, the X-intercept and the Y-intercept. Well, we don't do much with the X-intercept. The slope and the Y-intercept, though, ought to be easy in that problem. Why do I say that? Huh? Y equals 9.
No, I forgot a step. 3 times 1 is 3. So y equals 3x plus 6. So you have to do this.
Jessica, what are you doing?
Trying to figure it out, but I've lost myself.
Okay, back it up. Take the basics here. What kind of equation is that?
One step equation.
No. Is it a standard form equation? Is it point slope? Is it slope intercept? Oh, it's the most common one.
Points, no. Slope intercept.
Okay. So it's asking you for the slope and the y-intercept. That's already in the equation. You don't have to calculate anything. The slope is 3. The y-intercept is 6. What you're going to have to calculate is the x-intercept, because now you got to make y equal to 0. Remember the intercepts. One of them will have x equal to 0, and the other will have y equal to 0. But in slope-intercept form, you already got 2 of the 3. They're given to you in the equation form. The x-intercept is the hard one. Let me do this on the whiteboard. I'll show you what I'm talking about. It'll make more sense if I do that. So my equation here, y equals 3x plus 6. I already know that this is m, so that's my slope, and this is b, so that's my y-intercept, right? So that's 2 of the 3 items they were asking for in that problem. But if I want the x-intercept is in this form, x comma 0. The y-intercept is the opposite. Remember, it is 0 comma b. That's why I was trying to emphasize that earlier. Intercepts can be very helpful, and you'll see problems like this where you need to know both of them or know how to figure out both of them. So for the y-intercept, when I put 0 in here for x, I get y equals 6. So the y-intercept is 0, 6. But now to find the x-intercept, I got to make y equal to 0. 3x plus 6. Now I can solve for x. Take away 6 from both sides. Negative 6 equals 3x. Divide by 3. Negative 2 equals x. So our x-intercept is negative 2 comma 0. That one you do have to calculate. The thing is, though, even if we have a standard form equation, 4x plus 3y equals 12, I can do exactly the same thing with the zeros to find the intercepts. Substituting 0 for x allows me to find the y-intercept. Substituting 0 for y allows me to find the x-intercept. Lots to remember. See there, and there, the very next problem is kind of like what I just described. It's a standard form equation. It doesn't have the slope. It doesn't have any of the intercepts. So you could find the intercepts like I just described, but you're still going to need to do something different to find the slope. You're still going to need to solve it for y to convert it into slope intercept. That's the guaranteed way to get you the slope every time. This one, though, you got the graph. Should be easy to find the slope and the intercepts. All right, we got the y-intercept up here at 6, 0 comma 6. The x-intercept is 2 comma 0. Be sure you get the zeros in the right position. Think about what that ordered pair actually is, because it's not just the number 2 or the number 6, and certainly you can't write them together. You don't write 2 comma 6. That, to me, looks like a separate point somewhere else on the graph. That's 0 comma 6 and 2 comma 0. The slope, I would count squares, 1, 2, 3, 4, 5, 6 up and 2 to the left. So 6 over negative 2, slope's negative 3. I didn't even need to do that. I could have just gone right to here because there's 3/1.
So when you say count the squares, it doesn't have to be a full square,
They are all full squares. What do you mean?
like where the one,
They are all full squares.
No, like you're saying if it's
no,
cut
like
in
if
half.
the line hits the square like in the middle. you still
I'm
have
I'm
that
going I'm
line.
going straight up the graph line. There's no place on there where the line is hitting the middle. I'm not even looking where the line is. I'm not counting where the line is. I'm starting here where the point at 2 is, and I'm going straight up. I'm counting the entire squares. Because if I go up to this next line, that's 1. The next line up is 2. The next line up is 3. There's no fractions involved here. There's no decimals. There's no in between. I'm not counting up the line. I'm counting straight up the graph because that's the rise. Remember, rise goes straight up or straight down from a point. Run then goes left or right. We're not following the pink line along here to get slope because we don't know what that number is. We can't determine that because it's on an angle. You got to use geometry to figure out how long that is, because that becomes the hypotenuse of a right triangle. You know how to find the hypotenuse length? A squared plus B squared equals C squared. There you go. He remembers.
He's fresh out of high school.
Yeah, I learned
Uh,
that, I learned that freshman year.
okay, well, then you can come back and tutor some people then when everybody else here is doing geometry.
No, I don't want to be a tutor.
Oh, come on.
He's my tutor at home.
I've done Algebra 1 and geometry already.
Okay. So what would you do on this next problem? Find the y-intercept and slope of a line that crosses through those 2 points.
What would you do the y1 minus y2 over x1? Minus,
I would probably do y2 minus y1 over x2 minus x1.
You know what that is?
You said it backwards.
it's the exact same thing I said, but I just said it back.
Yeah, she said it backwards. Yeah, that'll give you the slope, and then what? Still got to find the y-intercept.
I don't know.
How did we find b before?
Y equals mx.
Right. Once you've figured out the slope, pick one of those points, do your substitutions, just like on that Jamboard, and solve for b. That's how you're going to find the y-intercept. Use that slope-intercept form to do your substitutions to find b. And so, like this page here is full of different problems to write equations from. And we're trying to get them all into slope-intercept form. First one, standard form, we're going to solve for y. What would you do with the second one? Okay, they're giving you the slope and 1 point.
Y would be 6 equals 2/3 times
0
Yeah.
plus b. But don't we already have the y-intercept?
Yeah.
Yeah, so why do you need to even do that?
Because I
I
like
was
to
thinking
make
the
my
same.
life difficult.
I was thinking the same thing.
Well, look at the wording too. It says you got this line that crosses the y-axis. Well, isn't that the definition of the y-intercept, where the line crosses the y? So they're giving you the y-intercept and expecting you to recognize either from the wording or from the fact that x equals 0. All I've just been talking about here with the intercepts and x equals 0, you get the y-intercept. So your equation would be y equals 2/3 x plus 6. There's no calculating involved if you recognize all that. If you don't, then you're still going to have to find b. And then you'll get to the end of the problem and you'll realize that, oh, they gave it to me anyway, because now I got x or b equals 6. It doesn't matter. It just takes more time. You know, one thing we haven't done very much of this last 2 weeks is word problems. Oh, I already heard the hate word. Jeez. But you know what? They're all going to follow the same pattern. They're all going to look like y equals mx plus b. So what's the variable? What's the mx part of this? Okay, which one of those is variable? The 50, that's your m, that's your slope. That's the rate of change, 50 per hour. Remember that clue word, per? That's a clue right there that you got the variable. So y equals 50x plus 80. Because it says in the end here, let x represent the number of hours for labor and y represents the total cost. Y is always the total because it depends on everything else that you do in the problem. The $80 is a constant. That's what B is. It's one spot. It's one number. It doesn't repeat. They're going to charge you $80 just to show up. So don't make these word problems more complicated than they really are, because we're still following that same format. It's all y equals mx plus b stuff. Then you got one with a table, write an equation. We just did some of that today. Now, what do you do with these parallel and perpendicular ones? Okay, parallel. 2 lines on the graph going along the same direction, the same distance apart forever. Do they have the same slope?
Yeah.
Yes. So you got the slope in one line. We're just going to borrow that. And so the answer is 2. Any line that's parallel to that one's going to have a slope of 2. So if you got to write an equation like in the second problem, we're going to borrow the slope from parallel. And then for 3, we got to use the other rule for perpendicular. Negative reciprocal. 90-degree angle. Crossing like a T. Negative reciprocal. So you flip that slope over, turn it upside down, and change the sign. The last problem on here says, are these lines parallel, perpendicular, or just intersecting? And how would you know? There's one thing you need to compare. Not the x, m. We just talked about slope. Slope's the defining feature of whether it's parallel or perpendicular. Parallel lines have the same slope. Perpendicular lines have negative reciprocal slopes. So no matter what the equations say, if you concentrate on identifying the slope and comparing those, you will know if those lines are parallel or perpendicular or just intersecting. But they're not in the same format, so you got to get them in the same format. You need to solve this first one for y and see if it has the same slope or negative reciprocal slope or some other slope. It's a multiple step problem that requires you to think through the definitions and know how to convert equations so you can do the proper comparison. Because it's all about the slope. Parallel and perpendicular is all about slope. 2 rules to remember. to add to the other 119 that I've already told you about this term. Maybe only 115. So that's it, ladies and gentlemen. We're out of time. End of the period. End of the week. End of week 5. 3 more to go. You guys better pass. I'm counting on it. Can't give up now. You've been here more than half the term already. Got to finish.
Told you at the beginning, I would get the graph.
So if anybody's got questions, send me a text, all right? Appreciate
Yes.
you guys all being here today.
Thank you. Thank you.
All right.